So let's kick this off because I think the first session is more of an introduction, slightly light, and then we can sort of get warmed up and get into the technical details as we go through the second, third session today. So this is a CFD applied course in motorsport. So we'll be focusing on the application of CFD in racing teams, especially in F1, because that's where we have a lot of knowledge from. Um, we're not going to look at uh, theoretical details in CFD. It won't get that heavy. That's not the scope of this, as Shubham mentioned. This is we have a different objective here, and hopefully we'll get there by the end of tomorrow. So just as an introduction, just a flashback to how did CFD come into F1. I just picked this up from an article. It says, I just read it out. Aerodynamicists have been aided immeasurably in their understanding by the advent of computational fluid dynamics, CFD. In 1990, the wind tunnel allowed downforce and drag to be measured, but couldn't show how the numbers were derived. CFD, which was then in its infancy and being looked at by Jeff Willis at Leighton House as a research project, would allow a spectacular increase in understanding the mechanisms behind the numbers and how they could be manipulated. So this is in the 90s, early 90s. I actually went and looked at Leighton House. This is the constructors during the early 90s. Leighton House is right there. Leighton House Judd with the engine manufacturer. 7 points that season. Not spectacular, but you can see what's going on with those cars. Quite interesting. You can see the end plate sweeping in board of the tire. You can see lots of details going on. And guess who was at Leighton House at that time? Adrian Newey. And Jeff Willis is just an interesting thing as well. I've had only one interaction with him, a phone call, when he was at Hispania Racing, which had a very short tenure in F1. And it's something I just wanted to mention because you try and contact a lot of people in F1, but people are busy. But Jeff, he was a technical director. He was doing everything at Hispania, probably, given the state they were in. But on a race weekend, he actually called me back for a half an hour phone interview, even though his team were in. They had some problems with the stewards with scrutineering on the weekend. But he called and spoke to me for half an hour on the phone about a CFD job at Hispania. It never came about because I think a week later they were gone. But yeah, just wanted to mention uh, Jeff, and then he's had a great career in F1. But yeah, that was my only interaction with him. Adrian, of course, our co-host here, has interacted quite a lot with him, possibly besties. No, yeah, yeah. So going back to the 90s, this was when CFD started coming into F1. A lot of even then it was quite low fidelity simulations, just local simulations looking at um, the flow field or what might be happening, just to try and understand and go back into the wind tunnel. And that leads us into a bit of a timeline. Uh, it's useful to understand how CFD entered F1 in the past, and how it's evolved into what it is now. Because as we go through the day, and I start talking about what people are doing now in the teams, it'll be nice to understand how we've got here. So yeah, as I said, in the 90s, we had 2D evaluations of wing profiles, diffuser shapes, almost very simple codes, and then it was a bit early for 3D CFD. It's just starting to look at it. And then in the 2000s, you started getting lots of RANs, steady state CFD. I think Sauber were one of the first ones. We had a supercomputer, and they were a pretty powerful one at that time. And I'll show you some interesting things from there. Um, and but everything took a long time. because pre-processing was intense. It took manpower, a lot of manpower, uh, not a lot of automation, a lot of error prone as well. It wasn't very robust. And then people are just looking at a few different car attitudes just because of how difficult the pre-processing was. And then moving on to the 2010s, a fairly good degree of automation, because that's when I started working around 2011 and 12 in F1. And even when I came into F1, they had pretty good automation, which only increased massively through that decade for pre-processing and post-processing. Uh, Turbulence model investigations, so specialized things for each teams. They are bringing in almost PhDs and researchers into the team fold to investigate this, having collaborations with universities to work with what they wanted out of a turbulence model, and also started running different different car attitudes, different investigations, and then this brings us to what it is now. It's an incredibly high degree of automation in CFD, almost to the point that we, as somebody who might enter F1 as a graduate, you might not even see what happens in CFD, a black box. So it's very good, and from my point of view, it's really good for engineers to have that background and deep understanding of CFD. And I'll tell you why as we go through these slides. Transient simulations are happening, not in mainstream production, just because of the regulations and the limitations that are imposed by the FIA. It's just too expensive still, but they are used to support a lot of activities with the steady state simulations. And most teams have their own bespoke post processing tools, incredibly fast, incredibly uh, automated, and just fantastic. Everything's about speed of analysis and just getting the next geometry going, and development at a very high rate. So yeah, just that leads us into what does an F1 Aero department look like? I think all of this hopefully helps you get an understanding of what an Aero department looks like, because I'm hoping some of you are thinking of a career in F1, and this should be good information for you. Um, it's a huge department, and the reason is simple: because it brings performance to the race car. At the end of the day, it's about making the fastest car. If Aero wasn't sensitive and not bringing performance, you wouldn't be spending money on it. But it does in this formula, and that's why we have these kind of huge Aero departments. They're well staffed, well funded, and extremely well optimized. Um, let's start with the development groups. These are the aerodynamicists. And what I've done is this is sort of the level of CFD ability, capability, understanding that you need, just from a scale of 1 to 3, that I believe for each group. So the aerodynamicists, they need a very good understanding, as you can imagine. In today's world, they may not need to do CFD. It's a bit of a black box approach, but definitely need to post process, understand, analyze, and be able to uh, come up with theories, and need to clearly understand the limitations of CFD as well. Then there's the CFD methodology group. These are the guys who maintain the software, the simulations. They make improvements. Usually, they're almost at the research scientific level. Obviously, they need an incredibly good understanding. And these groups have grown in the last few years quite a lot as teams take on more of the work. Instead of having the software supplier do it, they're doing a lot of it on their own, especially with OpenForm uh, uh, becoming an important tool, important software. It being open source and very conducive to F1 teams doing their own thing. So that is something that's grown over the years. Then there'll be a group called Aero Performance and Correlation, which almost ties these two groups together, but also they interact with the track aerodynamicists. Again, that's the reason I said they need quite a good understanding, almost at the level of the development aerodynamicists. Uh, I've been in and this group in various teams, so we've got a good understanding of what they do. The Aero Performance and Correlation group almost is they they bring together the track arrows, the CFD arrows, and the even experimental almost aerodynamicists. So it's a group that's very important. Not usually very large, but in terms of tying everything together and making sure that there's always they have their hand on the tiller almost. It's like they they know what's going on in terms of correlation if something is not right, and they bring in information from all three sources, from the track, from CFD, from the wind tunnel. There's usually an Aero software and HPC group. Again, this has grown large in some teams just because you're automating to such a degree and creating your own bespoke post-processing analysis tools. These are usually they have a software engineering background, so it's not, you don't have to just be aerodynamics and engineering background to be in an F1 aero team at the moment. These are heavily involved in the software development and also automation. And then on the other side, this is more operational. So you've got a uh, large amount of staff, wind tunnel engineers. So they look after the instrumentation, maintenance of the wind tunnel, making sure the repeatability is good, operation of the wind tunnel, because the wind tunnel is an absolutely complicated infrastructure. You are doing an experiment. You're doing, I don't know, 30 experiments a day or 50 experiments a day, and expecting your repeatability to be within, what do you say, Shubham? Half a point, less than half a point.
Well, at Red Bull, it wasn't that state of the art, I would say.
Okay.
Yeah, it was, yeah. I think a point maybe up and
Hmm.
down, depending on what changes and what changes are going on the car. If it's a floor, it's slightly different. If it's a front wing, it's slightly different. But yeah, generally repeatability was within a point, at least for downforce. That's pretty good.
Yeah, yeah, yeah. Good point. I mean, it does vary, as you say. I've been in, for me, the Sauber and Williams wind tunnels were excellent, and target was well below half a point for that. So yeah, those are the engineers that a lot of them have systems backgrounds, mechatronics, mechanical heavily. So it's a very interesting, very good job. You've got PIV engineers, and then they make sure that a lot of the tools like the total pressure rakes and PIV and all of the analysis tools that we use in the wind tunnel, that's all running and maintained and giving the expected results, and they keep automating a lot of that as well, so that as you do one run in the wind tunnel, you get, it's just an amazing and incredible amount of data that's at your disposal, and then you can then specify even more. You can ask for PIV, you can look for total pressure rakes, and yeah, and then you got 15 minutes, 10 minutes to analyze all that while somebody is changing a part before the next run goes. So yeah, those are the engineers that are working in the background to keep everything running, so that an aero engineer can go and do his development. You got wind tunnel operators and model makers. They 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 build the models. They also work with in the wind tunnel, doing all the part changes and all of that. They also do a lot of the setup before the model goes into the wind tunnel. The electronics, the all the data acquisition systems. They help with that, along with the wind tunnel engineers. Obviously, those are the two groups that make sure that the model is in a condition in terms of data acquisition, quality, and everything, and safety to go into the wind tunnel and be tested. Then there's model design, who are all the sort of the CAD designers that design the model. There's surfacing experts that they almost work with model. Sometimes they work in model as model designers. Sometimes they, and most of the time, they help with developing the car in drawing new geometry, along with in collaboration with the aero engineers. These these um, these people tend to be really good with drawing surfaces in CAD packages, which CAD packages are not normally the best at, but the expertise is, it certainly brings it to a very high level. And then the last thing I have is model manufacturing. So there's almost a whole manufacturing unit within the aero department for rapid prototyping, metal sintered parts, and some metal parts as well. Also, sometimes some wings and things are made out of carbon, so some molds and carbon layup, and yeah, it's quite an intensive group as well. So you
Yeah.
can see how large that
Yeah.
department looks like.
Yeah, before you move on, actually, just exactly that question, how large or how small? Because I get a lot of messages from people saying, I want to be trackside, I want to be doing like a lot of people don't know the difference between a CFD methodology department and an aero dev department, or at least don't know how to build their careers towards that. Um, what I want to do is basically go over each of them and let's just say aero dev, right, Puneet? In your experience, how big are aero dev groups? And I know traditionally
Yeah.
it's now changed, but traditionally you had front, rear, mid, right? So how big would these three groups be combined together at various teams that you went?
Yeah, each group. So if you average out the teams that I was in, I mean, I think almost all the teams had the same. You would normally have a team leader, and then possibly a deputy team leader, and then you'd have a mix of senior and aero and juniors, possibly 6 to 8 in each
Mhm.
team. And that's what I've seen. So that's
So
front, mid, and rear.
20, around 20 devs,
Yeah,
maybe
20 to
30.
between 20 and 30, depending on the team.
Yeah, between and 20. And then how big was the CFD methodology department?
I've seen 3. I've also seen
Yeah,
10.
I think at Red Bull there were like one, two, three, four, five of them.
Yeah,
That was the
yeah.
entire CFD group. So it's quite hard to get, and usually all of them have PhDs.
Yeah.
Usually all of them have PhDs. Aero performance and correlation. How big is this group?
It depends. Sometimes it's almost a blur between these two in some
Yeah,
teams. Uh, if you segregate them, I think this again would be for
four.
3 or 4 people.
Yeah, same here.
Right.
So
Yeah.
Red Bull again had like 4 or 5 people, which was a separate team, and as you said, they were the glue. Trackside aerodynamics. How big do you think this team is?
I've seen 4 or 5.
4 or 5. Wow, that's
Yeah.
impressive. I think Red Bull had like uh, 2 or 3, and there were the blur in Red Bull were aero performance and trackside
Yeah,
aerodynamics was
exactly.
the blur.
They
Right.
tend to work in both, and maybe that allowed them to just keep 2 track error. But if it's really
Yeah.
more segregated, then you might need 4, just because it starts getting pretty difficult to travel to every
Yeah.
race. Um,
Um, and then aero software and HPC. I actually have no clue.
mm.
Actually, I do.
So
I do.
when I started, there were 2. Uh, when just before I sort of came out of F1, I've seen 8.
Yeah.
Uh, yeah, so sort of completely dedicated to automation and bringing the data to your fingertips as soon as possible,
HPC
and
is
and
high
not just
performance
CFD,
computing.
yeah, and not just CFD as well as the wind tunnel data.
Yeah.
It's just software for the aero team, bespoke.
So this is basically software engineers.
Mm.
Mostly they are software engineers who are then bombarded with aero, a little bit of aero knowledge. You have like other groups like the CFD methodology department will teach them a little bit of aero. But this is actually where a lot of people who contact me from some of you might have friends from software engineering who are F1 fans, and this is the place where they go. And these groups are fairly large, because every team develops their own post processing tool, and a lot of teams also land up developing pre-processing measures. And
Yep.
like at Red Bull, we had like so many different post-processing tools. There were like web-based tools, there was a software, and then there are for wind tunnel, you require, they also interact with the wind tunnel software that teams tend to develop their own. So here is where people who are software developers get a huge opportunity to work. And now that AI has come into picture, and when I was at Red Bull, they were already hiring, young graduates for implementing AI and advanced data analysis and stuff like that. So this group is growing bigger and bigger in teams actually. Okay,
Yep.
let's move on.
Good. Yeah, I probably spent more time than I planned on this, but I think given the audience, I don't know the makeup of the majority of the audience. I would assume it's
Yeah, I
uh,
think this is our
people.
session. This is our
Yeah,
session in just massaging students. Some of these career questions. I know I spent time on this because I know these questions would be coming. So I said I
yeah.
might as well answer them right now.
Good. Okay. Okay. Let's start talking about how is CFD used in F1. So the answer is it depends on teams what their aerodynamic development philosophy is. It varies because you might think it's CFD straightforward. It's a simulation tool. It's used in a certain way, but it's quite amazing how it varies. And I've just put a few points together in two different columns here. Um, they're two different approaches almost. So on one hand, you have CFD used as a selection tool for going with tunnel testing. So you you do your work in CFD and you just use it almost like a filter to choose what you want to take to the wind tunnel and then test. So the aero improvement is judged in the tunnel before making the race car parts, and CFD setup matches the wind tunnel completely. So it's focused completely towards the wind tunnel. It's only used as a filter. The second approach is wind tunnel and CFD are used as independent and interdependent development tools because they have their own uh, pros and cons, which we can discuss later. Part selection for the race car is made in both environments. And the great advantage of CFD is that it can resemble racetrack as closely as you want, literally. And we'll talk about a couple of things and what I mean by that. So it's almost two different philosophies, and I've worked in both, and that's why I like to talk about this because it, it was not easy to adapt, switching from one to the other, and I saw how different they could be and how what kind of different results it could lead to as well. So it's quite interesting. I'm pretty sure Shub is has worked almost exclusively in this sphere on the right hand side here. Um, Red Bull is famous for doing that, and I did get a bit of experience of that kind of philosophy when I was at Toro. So, but a lot of other teams, maybe they're switching now. I've been out for a couple of years, but this is the predominant philosophy at most teams. Uh, with the regulations that the governing body imposes on simulations in F1, the CFD process is required to be a combination of incredible accuracy and speed, and that comes into play later when we talk about why we do only steady state simulations and things like that. So it's something to keep in mind. So that just leads us on to this whole question of automation and speed and what we do. So irrespective of the philosophy that I talked about in the previous slide, all aero departments want speed and accuracy for the CFD workflow. Uh, and as you can imagine, it is a balance. So you can't have both to its best extent. The CFD workflow is optimized to an extreme level to suit the demands of race car development. And I've seen different philosophies of giving up certain accuracy to achieve that speed. It's always a tricky balance, and I've seen extreme cases where speed is prioritized quite a lot, which it got to a point where it didn't make a lot of sense anymore. And I've seen a good balance as well. You've got separate groups working on different parts of the workflow, the CFD workflow, which I'll introduce in the next few slides as we go through. It almost results in a black box approach for aero engineers that are using CFD, so they can focus on developing the geometry of the car and spend all of their time doing analysis of the results from wind tunnel, from CFD, from the track. A lot of data is gathered on the track as well. But yeah, the result of this kind of, it's almost the high degree of automation and uh, we're trying to get as much speed into the workflow as possible. It's almost results into a black box approach where you don't really interact with only the CFD methodology group interacts with the internals of the black box. So yeah, you've got these three groups from the list that I showed you before. They get involved. The methodology group uh, do have a lot of focus on pre-processing and solver because they're intrinsically tied together. You need to have a very good handle on your meshing quality and robustness for your solver to work as well as it can. So the methodology group, they focus on this. Aero software, they focus on all the automation, pre and post processing. This is just going into the details of what some of those groups do. The Aero performance correlation group, for example, they look at the solution accuracy compared to experimental environment from both the wind tunnel and the track.